We'll now look into a simple Python-based example for logistic regression. Now for this use case, we leverage this old data which we have used in the previous modules, and that is HR analytic dataset, which we had downloaded from Kaggle for the previous modules. Let's jump onto Spider and load the data. So I presume you already have the data. Let's get started. I'll import pandas as pd, and I'll load the data into a data frame called newDF. Just for validation, let's look at the length and breadth of the dataset. So we'll say newDF.shape. And there we go. As we know, it has 15,000 rows approximately with 10 columns. And what are the new column names? That's it. Satisfaction level, last evaluation, and so on. Now, since this is a logistic regression example, we would need an independent value, at least one independent variable and one dependent variable. So the dependent variable needs to be categorical variable. Now from this data set, left signifies whether the employee has left the company or not, which can have values like 0 and 1. You can just do a quick check over here. We'll say new df, and new df will say left, and will say unique. Now it should return two values, 1 and 0. 1 indicates he has left the company, and 0 indicates he's not left the company. So if you boil this down to a simple use case, we can define a logistic regression equation, which is a classic example for a classification where we have an equation where y, being the dependent variable, is left, whether he has left the company or not. X is one of the independent variables. For simplicity, let's just assume we have one independent variable over here. So this satisfaction level seems like a good variable to be figured out. So the hypothesis would be defining employee attrition y as a function of satisfaction level. The general hypothesis would be employees with higher satisfaction levels generally tend to stay with the company, and employees with lower satisfaction level generally leave the company. So that's basically the hypothesis, or the framed equation. Now we need to import the logistic regression equation or function from sklearn. So we'll say from sklearn dot linear models, we'll import logistic regression. There we go. And just like we followed the process for linear regression, we'll first create an object for logistic regression, we'll fit the module, and we'll predict the outcome. Now to make prediction simple, what you can do is we'll create a trained data set and a test data set. The trained data set will be, let's say, the one which we'll use for fitting the line. And that will be, let's say, from this data set, we have around 15,000 rows. So let's take the first 10,000 into train and the next 5,000 into test. So we'll say new df, and we'll say ilog. We'll take everything up to the 10,000th row and all the columns. For test, we'll say new df dot ilog from 10,001 onwards, everything and all the columns. Now we will define test and train, and we have around 10,000 in train and 5,000 in test. It's like kind of a 60-30 kind of a division, not a very clean division, but then it's good for us for the moment. Now we need to create an instance of a logistic regression function. So we'll say LOR, which stands for logistic regression, is equal to logistic regression, and we'll execute this. So we have instantiated that into an object called LOR. Let's call the fit method. Now it's exactly analogous to the previous exercise. So we'll say X, which is, let's say, train, and we pass over here satisfaction level. And Y would be left. Alright, looks good. Now if I fit this, you might get an error because you only have one column and this gets converted to a series. So you just reshape that. Looks better. Okay, I accidentally put it as df, it's new df. Oh, it's a string. Yep, there we go. So we have created logistic regression object, and we have fitted the data set using the fit function. Now you can simply go and do a simple test. So we'll say logistic regression dot predict, and in predict, let's say we pass the entire test data set. So test, in fact, we can just copy this from the test data set. So we're just passing on the test data set as it is, and we get the predictions over here. And the predictions will be a 0 or a 1. There we go. We can see the output is 0, 0, 1 and many more, and ends with 0, 1, 0. So we have passed approximately 5,000 records in this test data set, and we will have an output with 5,000 rows. So let's keep this aside and let's understand how did it do a prediction. So similar to linear regression, we could just have the intercept values and we'll have the coefficients. And if you look at this, we now have the intercept and coefficient values for each of them, but for the object. I'll just do it once again. So we have the intercept of 0.75 and we have coefficients of minus 3.83. So coefficient corresponds to the impact of x on y, and intercept is defined as the part of y which cannot be explained by x. Now the equation will be log of odds of p upon p minus 1 minus p is defined as mx plus c, and we have the value for m and c. Now the predict function takes into account this equation with the values of the parameters, does the necessary transformation so that it can predict the probability for an outcome, and from the probability it takes the cutoff as, let's say, simple 0.5. So anything above 0.5 would be 1, anything below 0.5 would be 0, and vice versa. So that is where we have the outcomes when we do a simple predict function passing some new data sets. So it calculates the prediction value as probability cutoff at 0.5. So what if you were interested to understand the probability for each of the classes when you're doing a prediction? We can simply call another function called, instead of predict, we can say predict probability. Just short from PROPA. And now I can see you can actually have the values for each individual record. So if the value for one is 0.56, the probability of one is 0.56, the probability for the other one would be minus 1 minus 0.56, and we have a corresponding values over here. So this is a simple demonstration for a logistic regression example where you have one dependent variable and one independent variable. Now let's take let's take this one step ahead. What if we want to define this equation in a little lengthier way? So we have more than one independent variable. So we'll say, okay, the attrition of a company is defined as a function of satisfaction level, and let's say another variable like time spent with the company or number of projects he's worked with. So if you just do a simple columns again, we'll get the list of columns that is associated with this data set. And we've already have satisfaction level. Let's take time spent with the company or number of projects, right? So let's just recreate the same logistic regression function over here. So instead of saying fit with one variable, I will pass a data frame with two of them. So I'll say satisfaction level and number of projects. Number project. Right? Makes sense? So this would be a data frame. So we don't need to vary shape. So this will have a shape of two columns and let's say around 10,000 rows. So fair enough. Now if we do a fit, there we go. We have the equation done, created for us, and we can quickly go ahead with the fit function, predict function. So let's do a predict over here. And if we do a predict, we'll do the same over here. Instead of passing just one of these columns, we'll pass two of them. Right? There we go. All right, I have to remove this. Yep. And we have the outcome over here. So the outcome might be a little different compared to the previous one. So if you remember, the previous one was 0, 0, 1 and kind of ended with 0, 1, 0. And here we have a prediction for 0, 0, 0. Now, this might not be same if you have more number of variables. The moment you add more number of variables, in some cases, the algorithm learns better. So we can say that there's kind of an improvement in the algorithm. Not we can't say that for sure because we've still not reached the point where we have started evaluating machine learning models. We'll soon reach there. But then just assume that the moment you added one more variable, you see a fair amount of differences in the outcome. Now, just let's have a look at the intercept and the coefficients. So, to look at the intercept, we have an intercept of 1.22, it's changed. And let's look at the coefficients. Now, we have two coefficients for two variables. And there we go. One of them is minus 3.98 and the other one is minus 0.10. So definitely you can say satisfaction level has an extremely high impact compared to number of projects. Now if you add more variables, you have a better equation getting created in some cases. I mean, please don't take this blindly. You don't necessarily add n number of variables just to increase the accuracy. We'll get to those details later. But then you can see, the moment you added one more variable, the equation kind of changed. You see differences in the intercept values and the coefficients. You can kind of make an understanding of how does impact work over here. So that was a basic example to understand a logistic regression where you have one independent variable and two independent variables. So if you do a simple recap, we started by understanding what is logistic regression. We looked into the scenario where we need a workaround to convert the logistic regression equation into into a different way where we use log of os to represent it as a continuous function. So the jugaad over here was done using the logistic function, and that's why we get the output in a format of probability where we'll have values between 0 and 1. Now, after looking into the basics of math, we also took into account a simple example to understand how does logistic regression work. We took one variable for an example with satisfaction level, then we took two independent variables. And we can repeat this exercise probably for n number of independent variables. But that's it for now. We'll get into more details of logistic regression, where we'll come to the point where we'll understand evaluating machine learning models. So we're good for now. Let's move on to the next topic.